Have you ever wondered why your phone gets hot when you use it, or why a car engine makes so much noise? Or hey, why can't we just build a machine that runs forever, with zero waste? Well, it turns out the universe has some pretty strict rules about that. Okay, let's get into it. So this is the big question, right? Why can't we build a perfect machine? I mean, from the biggest power plant down to the phone in your hand, every single thing we've ever built is, at its core, unavoidably imperfect. But why? Okay, so at the heart of it all is this simple idea. You put energy in to get useful work out. But here's the catch. No matter what you do, some of that energy is always lost. It usually just escapes as heat. And this isn't just a design flaw we can fix, it's a fundamental property of the way our universe works. To really get to the bottom of this, we've got to tackle a huge idea first, this myth of 100% efficiency. So let's break down what that word efficiency actually means when we're talking about physics. Thermodynamic efficiency is, well, it's basically a report card for any machine. It's just a simple score that tells you how much of the energy you pump in actually does the job you want it to do, compared to how much of it just gets wasted. So a perfect score, a 100%, would mean zero waste, absolutely none. So how do our real-world machines actually score on this report card? Well, it's kind of shocking. The engine in your car, it's only about 25% efficient. Yeah. That means a whopping 75% of the energy from the gasoline is just lost, mostly as heat. Even a gigantic, state-of-the-art coal power plant barely gets to 46%. We are nowhere close to that impossible 100% mark. So what's with all this waste? Why is it everywhere? Well, the first big reason is a law of physics that you just can't argue with. You can think of it like a universal tax on every single energy transaction that ever happens. And this is the big one, the second law of thermodynamics. It's a fundamental rule of the cosmos. And what it says, basically, is that the universe as a whole is always getting messier. It's always moving from order to disorder. And every time energy changes from one form to another, it adds a tiny bit to that total cosmic mess. And that messiness, it has a name: entropy. Waste heat is pretty much the main way that machines pay their entropy tax. It's the unavoidable, messy byproduct of doing useful work. And here's the kicker. You can never get that wasted energy back to do the same work again. It's a one-way street. The process is irreversible. This brings us to the practical problem. To actually get useful work out of heat, like in a car engine, you need a temperature difference. You need a hot place and a cold place, or a sink. The engine is physically forced to dump some of its energy into that cold sink just to keep the cycle going. And that dumped energy, that's your waste heat. That's what makes 100% efficiency physically impossible. Okay, so mechanical things like engines are out. But what about something with no moving parts? No friction, no fire? What about the clean, logical world of a computer? And you'd think so, right? I mean, if a machine is just flipping ones and zeros, where could the waste possibly come from? Can't we make that process perfectly efficient? The answer, incredibly, is still no. And this is where things get really mind-bending. It's called Landauer's principle, and it says that information itself is physical. And whenever you do something that's logically irreversible, like erasing a bit of data, which is basically the computer equivalent of forgetting something, you have to pay a tiny but very real energy price. And that energy is released as heat. And this is the bill. This little formula is the Landauer bound. It tells us the absolute bare minimum amount of energy it takes to erase one single bit of information. Now, it's an absurdly tiny amount of energy, but the crucial part is, it's not zero. That's the whole point. Even the simple act of forgetting has a physical cost. And here's the reality check. As tiny as that physical limit is, our computers today are, well, they're wildly inefficient compared to it. They waste thousands, even millions of times more energy for every single operation. Just think about that next time you hear about how much energy data centers use. A huge chunk of that is just the cost of processing and, yes, erasing data, the cost of forgetting. So we've got limits from physics, and we've got limits from information theory. But there's a third layer to all this: the messy, practical reality of actually building things. Sometimes, machines are imperfect simply by design. This is a really cool way to look at it. On one side, you have engineers. They try to build something based on an ideal blueprint, but they're always having to make compromises, balancing performance, cost, how tough it is. On the other side, you have nature. Nature doesn't have a blueprint. It's just blindly optimizing for one single thing, passing on genes, even if that means the animal itself is kind of a mess.
Both approaches are full of compromises.
And for engineers, these compromises, these constraints, are everywhere. You're always making trade-offs, like sacrificing some efficiency to make something cheaper. You get stuck using older designs because you can't just start over from scratch. That's called path dependence. Or maybe a machine that works great in a lab performs terribly out in the real, messy world. Perfection always gets traded for practicality.
And sometimes, these little imperfections can have huge consequences. Take the massive 2003 Northeast blackout. That wasn't caused by one single catastrophic failure. No, it was a cascade, a domino effect of smaller issues, design limits, and weird environmental factors that all lined up just right to bring a super complex, highly engineered system to its knees.
So look, if perfection is impossible, then what are we even doing? Well, this is where the story completely changes. It stops being about our limitations and starts being about our incredible ingenuity.
This quote really gets to the heart of it. It points out a different goal. The lesson from nature is that instead of trying to build one single perfect but brittle system, it's way better to build resilient systems, systems that have backups. A system that can degrade gracefully might lose a little function when it's stressed. Think of an airplane that can still fly even after losing an engine. But it doesn't just shatter into a million pieces. It bends, it doesn't break.
And that, right there, is the real takeaway. The whole point of great engineering isn't to defy the laws of physics. It's to be clever within those laws. This isn't a story about failing to reach 100%. It's a story of incredible success, of building things that are robust and resilient and good enough to literally change the world, even with all their flaws. The most brilliant designs, they aren't perfect, they're tough.
And so that leaves us with this final thought to chew on. If we stop chasing the ghost of perfection, it forces us to ask a much better, much more important question. What does building a better machine actually mean? Is it more efficient? Is it more resilient? More adaptable? That's the real challenge for the future of technology.